This is often called the most important algorithm of the 20th century. Without Fourier transform, and specifically the FFT or the Fast Fourier Transform, we would have not have Wi-Fi, 5Gs, JPEGs, MP3s, MRIs, or even noise cancelling headphones. So we need really to understand what Fourier transform is and how it's done and why is it actually a thing. Okay, so we are gonna start with an analogy. Analogy is going to simplify things. It's not gonna be going with too much with signals and things. So let's say we have a smoothie. Yeah, a smoothie. If you taste it, you will experience a mixed flavor of tastes in each moment in time. Yeah, so this exact taste that you have experienced, a mix of tastes in time, this is the signal. Yeah, if you want to know the recipe, you want to know exactly how many grams of strawberries, banana, yogurt, milk, that you have to understand in things in a specific of this signal, which is frequency, which is a stamp of time. So in the time domain, which this is a smoothie, as you drink it, the signal amplitude changes over time. Yeah, so it's a signal, and this signal changes the amplitude by time. Yeah, it's a signal that changes amplitude by time, a mix of flavors on by time. So let's say on the beginning of the cup, you feel more strawberry than milk and a mix of banana, but here you may feel strong feeling of banana, let's say, and there is a strong feeling of strawberry, the strongest. So it's a mix of these, which is a mix of juices, and these juices we are going to simplify as signal. So this signal is a mix, or this juice is a mix of juices, so it can be become as a mix of signals. Let's say it can be a strawberry one plus a banana one, yeah, plus milk, yeah, so it can become a mix of signals. And here where Fourier transform gets its idea. Okay, so it's a mix of signals, and in that instant instant of time is called frequency. Yeah, it's measured by Hertz. Hertz is a scientist that his name is simplified as Hz, which is frequency. Okay, measures the frequency. I guess we know that one. Okay, so in the time domain, the smoothie is, when we drink it, the signal amplitude changes over time, but in the frequency domain, this is the recipe. Yeah, this is where the list of ingredients and their amounts come in. So let's get in the Fourier transform. This is in the machine that takes a smoothie time signal and unmixes it into the recipe or the frequency spectrum. This provides a mathematical miracle. Any signal, no matter how complex or jagged it is, can be constructed by adding together simple sine and cosine waves of different frequencies. So yeah, most of the signals are so this signal, as we said, it has become a mix of a sine and cosine. It's a sine or cosine, it's the same idea, but as being a sine is shifted of the cosine by 90, and same for the sine. Sine is a cosine by shifted. Like if we saw the sine wave starts from the origin and goes up and down. Yeah, if we find the cosine is starting from the 90 and goes down and up. Yeah, so this is cosine and this is sine, sine of theta, and this is cosine of theta. Yeah, so it's just that if we shifted that part by 90 or by pi over 2, we will find that we start here by a sine. Like this is a sine again. Okay, yeah, so again it's a mix of sine and cosines, all these waves. Okay, so now we get to the mathematics. So to an engineer, the transform is more of converts the function of time, which is gonna be an ft, to a function of frequency. An ft is going to become a function of time domain, which is usually represented by f hat of theta. It's just theta is usually drawn like that, or for simplicity, you can just do it capital F O of omega. Yeah, this is, I guess, more simple to draw. Okay, so the formula of the continuous Fourier transform is where f hat, or we're going to draw it now as f omega, becomes as integration of negative infinity to infinity. This is the entire negative infinity to infinity means it is the area under the curve, all the area under the curve, all this section under the curve from negative infinity to infinity. So it gets all this section, yeah. F of t, yeah, e power negative 2 pi I omega t dt, yeah. All of these are going now to be broken down. So let's get to the parts here. So breaking this down, that f of t, which is this part, this is the original input signal, yeah. We did the integration on this original signal, this signal, yeah, this signal. This is f of t by t, yeah, for the time domain, yeah. So, and e power negative 2 pi I omega t is the Euler formula in disguise. It traces the circle in the complex plane. So it's a circle, or the unit circle in a complex plane. It traces it, yeah, to it essentially winds the circle around this signal around the circle at a specific frequency, which is omega, yeah. The integral is the sums up the mass of the signal after winding it in the area under the curve. The result, which is going to be f of omega, is the signal has a strong component frequency omega. This integral will be large, a spike in the graph. If that frequency isn't a signal, the integral sums up to 0, yeah. So now to the actual algorithms themselves. Now we're gonna go with the algorithms of D, F, T, and F, F, T. These computes, the computers cannot handle continuity in infinity. Like computer cannot do that integration from infinity to infinity. It's complex on us as humans. So let's imagine for computer, we need to do a code for each integral like that. No, it's not a good thing to do. So you will need something that the computer can understand, yeah. It handles discrete list of numbers. This gives us a discrete formula of discrete Fourier transform, or DFT. So the problem with DFT, if you have a signal of n points, you have n points and m points, and you have checking the frequency requires n square operations, yeah. So it's a complexity of O of n square, if you are interested with that. So if n equal 1000, so the complexity or the operations to be doable, it's going to be a million here, yeah. It's going to be a million. So as a 1000 here is like a 1 megabyte, let's for instance say, or 1 kilobyte even. It's not even 1 kilobyte. It's like a typical audio file. It would require, or it's gonna require a million operation. Yeah, this would be too slow. Yeah, for just an audio file. So imagine if we are doing for a long video, or yeah, it would require our strong PC. So the solution, the fast Fourier transform, has came in place in 1965 by Cooley and Tukey. They popularized this f of t. It uses something called divide and conquer. Yeah, conquer. So this strategy is based on the Danielson-Langstot's lemma, as if I can remember the name, to reduce the complexity of O n square, which you have just spoke about, to become O of n log of n. So this is 100 times better. So let's say if we return again for our example of, let's say, our previous example, let's say n now is a million. It's not our previous, but it's more even than our previous. It's a million. The DFT is going to become about 1 trillion. 1 trillion. But the FFT here is going to become only 20 million. 20 million. So this is way less. We're talking here 1 trillion. Here we're just added 20 instead of this one. So that finalizes our third part, talking about which is better, which is have saved our transform. So now for the step-by-step execution, we are writing the code to analyze the vibration sensor. We're not gonna write a code, but we're to analyze a vibration sensor or on a bridge, like any engineering signal. These are actual steps. So let's say the first thing we do is something called sampling. Sampling is done to transform from analog to digital. So you must capture in a real world signal to a discrete sampling frequency. Like say if we have a wave like this, it's like that way. So we want to do it as sample. The more samples we get, the better the quality. Let's say name it quality for now. It's the better the quality. The more samples you take, the more the more loss you take here. The more, like say if we took a small one, this is a less loss here. So we need more sampling. This sampling is constrained by something called Nyquist, one of the most important theories in communication, Nyquist Theorem, where you usually take it in microwaves or things like that, or digital signal processing. You must sample at least twice as fast as highest frequency. Like you want to capture. So let's say if the frequency here is 20 kilohertz, this is usually the average of an audio file. You must sample it at 40 kilohertz or more plus. So how do we even know the frequency? Like I guess I've skipped that part. We just do, this is on the time domain. So we just do the inverse of the time is the frequency. Like how many frequencies, how many times we did something per time. So how many times you did eat an apple in 10 seconds. So we do 1 over 10. This is frequency. So what we're doing here by seconds. Okay, so we need to make the frequency, if we're sampling over 40 kilohertz, we need to make samples even greater than the frequency we have used here. Second thing is the windowing. Second step, the real-time signal are infinite, so but we need to take a chunk. This chunk is going to be on the y-axis. So let's say we have took 1004 sample. This is also a standard. Cutting a signal ambiguously causes spectral leakage, or as we call it, noise. We need to know when we take it. So apply the window function like a Hamming window. It makes these edges signal to 0 smoothly. We don't want. Let's try, like if you have Audacity or some audio changing application, and you tried 1024 bits and the other bits out there in the app, you will find how smooth the video becomes. It's not like it becomes like not my voice. It gets even better. So the last thing, the FFT algorithm, it's gonna become that the computer performs this algorithm and splits divides the n samples into 2 halves. The n, it divides to 2 halves, even indices and odd indices, odd and even, and it does recursion, splitting these halves into 2 groups of 2 samples. And then we do something called the butterfly operation. It's like something that was complex. You will take it in the college if it's on you. If it's a part of their curriculum, it's a very beautiful thing. it took the two small points of by the DFT back together to do the FFT, yeah. So using something called with twiddle factors, then you merge up these results and bubble up to the full spectrum, yeah. So it's something that the computer does. You don't really need to go beyond theory, except if you are a specialist. Then the last step is magnitude and phase extraction. So the output of FFT is a complex number, like a plus b of I, yeah. So when we need to do find the values in a complex value, we need to find two things: the magnitude and the phase, yeah, the phase. So the magnitude here is square root a square plus b square, and the phase here is arc tan or negative tan of b over a, yeah. This for me represents the how loud the audio is, and here it represents the timing and shift of the wave. So yeah, so in a real world engineering application, a signal processing removal, let's say we want to record a pilot's voice in a cockpit, but there's a loud 400 hertz hum in the aircraft power supply. So the Fourier fix is gonna be to run an FFT and to see the spectrum. Then you will see the massive spike exactly at the so you'll see an animation, and you'll find not this was the time, and you'll find the animation as like that, as a single frequency, yeah. This is the noise for me. This is gonna be the result exactly at 400 hertz. Zero out the specific bin in the frequency domain, and then run the inverse FFT to get the audio back to the time domain. This voice remains and the hum is gone. And that's how usually the filtering is done in applications like Discord, WhatsApp, Messenger. All these great apps and big apps use, even our mobile phones use in our calls, these things without us even knowing, using in our processing, doing the DSP or the digital signal processing. Yeah, so the health monitoring. So let's do a scenario of a skyscraper. Scraper vibrates during wind. So the Fourier fix, let's have a skyscraper. It's not gonna be drawn so wrongly. Wait, so let's say this is a skyscraper for some reason. Yeah, and this, oh no. So let's say this is skyscraper. Yeah, it's gonna be better now. And this skyscraper is it vibrates during the wind. So the Fourier fix is gonna using something called accelerometers, yeah, to measure the vibration of the FFT. Reveals the building natural frequency. When the building is stable, yeah, it's static. If these frequencies shift over a year, it indicates a structural damage, like stiffness or whatever the construction people would call it, but I guess, yeah, it's stiffness of the building. Let's do another example in image compression, like in JPEG. A photo of 50 megapixel megabyte. We need it to be 2 megabyte using in compression, yeah. In compression, we break this image into 8 by 8 pixels, like 8 by 8 pixels, yeah. And after this 8 by 8 pixels is done, we take a 2D Fourier transform. Here it's called DCT for each block, for each of these blocks. Now the FFT reveals that the high frequency theta or sharp changes in color are invisible to human eye. The human eye sees a specific spectrum of things, like in audio. Even in audio, we see like from, if I remember, from 20 hertz to 20 kilohertz, if I'm not mistaken, yeah. From 20 hertz to 20 kilohertz. So if you got a speaker that makes you hear over 20 kilohertz or beneath 20 kilohertz, you won't even hear any of these. And other animals like dogs and things like that can hear that. we 20 hertz is the full bass, like this is the actual bass. If you have a speaker that has 20 hertz, this is like deep bass, yeah. So it reveals that frequency data and sharp changes in color beneath that and above that, but we're not talking here audio, we're talking like yeah, we're talking video or image. We throw away these high frequencies or super low frequency, and save the like this saves like 90% of the space, like strangely, because that all of these things are beyond our listening, and sometimes are so beneath our listening, if we are talking audio, of course. So, and the last thing we're going to like an example give an example of is going to be 5G and Wi-Fi. So, and 5G and Wi-Fi sending data over the air, like Fourier fix, instead of sending one fast stream of data, like just giving 10 gigahertz at instantly, this is something not that good. This makes gives too much power and needs too much power and can be lost and hits echoes, interference. We send thousands of small streams. We send so many small streams as this of different frequencies as the receiver now uses the FFT to separate these thousands of overlapping audio radio waves instantly. So that's how the audio is being received, or the videos are being received, or even the Wi-Fi sending and receiving things is done. This is something like you will find in TCP, transfer control protocol. Something like it separates the signal, but like not really it's the same way, but it's not the same. It's the same concept, but not the same way, because there's handshakes and this is segments and things. But here I mean like you can separate things out. It's like audio, video, and like that. So here was everything we have talking about in the Fourier transform. I hope that you like the video, and if there's something you don't understand, I would love to hear questions. And thank you for your listening, and I hope that was useful. And thank you for your time, and bye bye.